okay?
Yeah.
All right, so good morning, everyone. My name is Mona Hella. I'm a professor at ECSE. The first slide that you see here just has a picture of the campus. Let me again put my, not sure if you see my, my cursor. A picture of RPI in the fall. This is one of the prettiest time of the year. And these are pictures of the students that I've graduated over the years. Fortunately, it doesn't show my current students. I currently have 6 students who are working on the projects that I'm going to explain in the next slides. This is just a summary of what I do. Basically, I'm a chip maker. I do integrated circuit design for various applications. So really touching on what Professor Datta has just said, which is like use cases based research. I develop solutions in an integrated format for next generation communication for sensors, and then I use power management to provide energy to these applications. My power scale is much lower than what Professor Luigi has been talking about. So the power here is limited to anything below 1 watt. So for communication application, I work on beyond 5G and also on optical communication, visible light, and so on. And for sensors, I develop terahertz sensors for health and additive manufacturing, time of flight sensing, and so on. So the first application that I'm going to show is maybe something that would be of interest, and this is on continuous health monitoring. So trying really to move beyond the hospital to doing stuff for personalized medicine, which I think probably is really needed right now when we are running out of beds in hospitals. So typically in the hospital, you have high quality equipment, but they are bulky, they are expensive, and they need trained personnel. There are also people who need this to be at home, but typically it is really, really big in size and not comfortable for long-term monitoring. And what we are trying to work on is developing these microchips that can be attached to the skin or as part of the clothes, like wearable electronics, and can provide the same functionality as the hospital-grade equipment. So why do we need continuous monitoring? It's not about measuring blood pressure or measuring anything as a data point. No, you want to be doing that in real time and measuring it over a large time scale to be able to detect irregular activities. For example, heart problems, problems with the brain signals, and so on. So I'm going to be going quick given the time. So the system that we develop on a single microchip would receive these biological signals. These signals tend to be really very small in the microvolt to 1 millivolt, so very close to the noise levels. And they also can have peaks, so you need to have a wide dynamic range electronics to deal with them. They are located in the lower part of the frequency range, typically below 400 hertz. That's another problem, because this means that you are susceptible to 60 hertz noise from the lines. So you need a wide range analog electronics, and then you need also analog to digital conversion, and then communication, which is probably part of a microcontroller, and then transmitting the signal with an antenna. And of course, you need power management to make sure that this is battery operated, or you are operating based on energy harvesting. So this is the chip that we developed, and it's a 2 millimeter by 2 millimeter. This is a picture of my students. I didn't show my lab, but my lab really has all electronic instrumentation from 0 hertz up to 500 gigahertz. So we do low frequency designs and we do high frequency designs. This is a picture of the low frequency capability, which has a signal analyzers, logic analyzers, and you can see here, these are the students measuring ECG, which is the signals for the heart, EMG for the muscles, and EEG, these are for the brain. So other projects, when I started at RPI and when my PhD, I was working on wireless communication. So this is something I continue to work on. And I think it is really very valid these days as we are all cramming on whatever communication infrastructure we have. Those people who argue that we don't need additional bandwidth, I think this is now the time to say that yes, we do need additional bandwidth if we're all going to be working from home and basically doing everything from home. So sharing the limited amount of resources, we need to be transmitting data in the hundreds of gigahertz, and we need additional bandwidth. This is not just for data centers, but also for the Wi-Fi that we have at home. So these are pictures of above 100 gigahertz communication systems that would really ideally be used as access points in any indoor environment and providing data above the 100 gigabit per second. One of the problems associated with working at very high frequencies is that these are all line of sight. So it means it's there has to be some sort of a beam steering and also beam tracking. And I think this couples with what Professor Daria and I think other faculty are going to talk about, is that the network itself might not be reliable. And there's going to be a certain amount of delay in locating different users and pointing the beam at them. So once all these are finalized, they can also be integrated in the chip. So this is what I'm showing here is just a single link, which is very small, 1.4 millimeter by 0.8 millimeter. And the cartoons that I'm showing here is what we call an eye diagram, which shows different types of modulation systems when applied. These ICs that will be developed for future communication systems, relying on having phase shifters, power amplifiers, up conversion, and integrated antennas, which is really the reason why we want to go to these higher frequencies, is that you have a massive amount of bandwidth available, and you can integrate large arrays on a single chip because of the size of the antenna. All right, so this is all called 6G, and it's really building on the advantages for 5G, but taking it further higher in frequency and really much higher in data rate. Another also communication system that is similar in principle to beyond 5G is using free space optics. But this time not using lasers, but using LEDs. So the light that we already have at home, especially with now having solid state lighting, this can be modulated at much higher data rate and using similar principles to line of sight communication. And you can get all the advantages of security, because you have to be, the transmitter has to see the receiver, and at the same time you have a massive bandwidth. You don't have any problem with interference with others, and it is pretty secure. And this is an example of some of the microchips that we built. These microchips we design, and we do the layout, we send it to the fab for fabrication, and then we test it. So this, again, this is a picture of another lab that we have. We have labs in the Johnson Engineering Center, which is where the ECSE department is. And there's also another center, Center of Integrated Electronics, or Center of Material Devices and Systems. This is another building where we have the optical setup as part of the LISA Research Center. The chips, yep.
You have to wrap up in
sure.
next 30 seconds. Sorry about that.
No problem. So this is an example of applications. So we can use these high data links to communicate between two buildings, or to use it in the stadium where we are all sharing the same bandwidth. But in this case, the LED and the lights from the stadium can just be applied to individual users and deliver massive amount of data rates. Right. The last thing is terahertz. For those of you who don't know what is the terahertz, is the frequency range from 100 gigahertz up to 30 tera. and we are using this for gas sensing. This is again another setup that we have. We are using it to detect volatile organic compounds. So basically, this is what exists right now in the market, but we are trying to build system on chip. So we have system design, circuit design, the chip design, and then finally we put it in a setup, and this is an example sensing methanol and ethanol. All right, and I think this is my last slide. I also work on energy harvesting. So I collaborate with faculty who build micro electromechanical systems as harvesters, and then I build the control loop around it, and this is used for wireless sensor network. And I'm done. And if you have any questions, please email me. Right? Thank you very much.